Right, so last time we looked at the differentiation of trig. Let's go backwards. Let's go the other way. So if now I want to integrate cos. Now in this case I'm just saying, well, the angle is a linear function. If I was going to integrate cos, well, let's think about this carefully. When we differentiate sine, we got cos. Therefore, then when I integrate cos, I'll get sine. The 1 over the a, it'll always be 1 over the coefficient of x when I'm dealing with a linear function, because ideally we would like the derivative out the front, which would be a. Alright, sine, this is where we've got to be careful. When I differentiate cos, I get minus sine. So therefore, when I integrate sine, I get minus cos. So as I say, now this is where we've got to be real careful, because when we differentiate cos, we get minus sine, but when we integrate sine, we get minus cos. It's very easy to get those the wrong way around. So make sure, and if you're unsure, of course, have a look at the reference sheet. An integral of sec squared would be tan. Alright, so integral of sine 3x minus 1/3, sine now goes to minus cos. Don't forget your plus c. Cos of 1 minus 5x, coefficient of x now is negative, so we're going to have minus 1 over 5, cos goes to positive sine, so it stays negative, and the angle doesn't change, so 1 minus 5x plus a constant. And let's do a sec squared one, but the coefficient of x in this case is a half. 1 over a half would be 2. The sec squared will go to tan. So there's some, well, basic ones. Let's integrate a definite one, sine 2x. Okay, that's going to be minus a half cos 2x. And we're going from pi on 6 to pi on 2. Remember, whenever you're dealing with calculus and trig, radians, got to be in radians. So pi on 6 to pi on 2. So minus a half, subbing in we get cos of pi minus cos pi on 3. Cos of pi, I'm thinking of our graph, that's negative 1? I think that's negative 1. And cos of pi on 3, now whilst it's radians, I still think degrees, pi on 3 is 60 degrees. Cos of 60 is a half. So we get minus a half times minus 1 minus a half. It all ends up to be 3/4. This one here, okay, back to this idea of let's create the derivative out the front. I need the derivative of the angle in this case. Derivative of x squared is 2x, so I've got a half of 2x sec squared x squared, so that will become just a half of tan x squared. So same as we did with exponentials, same as we did with the log functions, we want to create the derivative. Sine squared x. They love asking sine squared or cos squared somewhere in the paper. I cannot remember the last time there's been an Extension 1 HSC and that question or variation of it hasn't been there. Because you need to remember your double angles in order to solve it. So sine squared, well remember, cos 2 theta, double angles. Different ways we could do it. We could say it's cos squared minus sine squared. But if I write it as 1 minus 2 sine squared and rearrange it, that means sine squared is a half of 1 minus cos 2 theta. If it was cos squared I was trying to integrate, then it'd be a half of 1 plus cos 2 theta. So I can now rewrite this integral as a half of 1 minus cos 2x. And I now get a very simple trig function to integrate. Integrate the 1, of course, we get x. And that's what I was saying before, that, hey, sometimes we might get an x. If this was a definite integral, sub in 45 instead of pi on 4, we're going to get completely the wrong answer. So it must be working in radians. Minus a half sine 2x. Whether you expand that out or not, I mean, it's up to you. I mean, the second last line is probably good enough for an answer there. Okay, integral of tan x then. Well, if I rewrite tan x as sine on cos, I now have a situation where I can create derivative on function. It's not quite there, because the derivative of cos is of course minus sine. So I could rewrite that as the minus of the integral of minus sine on cos. But I now have the derivative on the function. So I know it will be the minus the log absolute value of cos. Remember, sometimes our cos function could be negative and you can't find the log of a negative number, plus a constant. If you prefer, and I must admit I do, rather than writing as minus the log of cos, I could bring that power in, cos x to the negative 1, well, reciprocal of cos is sec. And you get the log of sec x. As I say, personally I prefer to write it that way, but it's up to you. The reality is, if I get the integral of tan x, I'm just writing that answer down. It's not a standard integral that they give you, but I tell you what, it's well worth remembering, because it's surprising how often that comes up. So you save yourself a lot of time if you just know. I mean, integrated tan is log of sec. Okay, ooh, cos x, sine x is to the power of 7. This is another one of those ones where we want to write it as derivative times some function to a power. Well, the function to the power of sine. The derivative of sine is cos, so actually I've already got it in that format. I don't have to do anything. So it must be add 1 to the power over the power. If you don't see it straight away, remember you can do it via a substitution. You say, well, what's causing me the problem? The sine to the power of 7 is, so I'll make u equals sine x to u equals cos x. Oh, but now I've got to change my limits. When x equals 0, u is the sine of 0, which is 0. When x is pi on 2, u is the sine of pi on 2, which is 1. And so it will become the integral from 0 to 1 of u to the power of 7 to u, and that's when, if you hadn't seen it before, now you go, oh look, it's just add 1 to the power over the power. So we get an 8th of u to the 8, but seeing I've changed my limits, I don't have to substitute back in the sine x. I can just sub straight into this one, and we end up with an 8th. Had I spotted that it was in the format of derivative times function, then I could have just straight away gone and said, oh, that's going to be an 8th of sine x to the power of 8. Bang, I've got that straight away, essentially, but then I'd substitute in pi on 2 and 0 instead of 0 and 1 and get the same answer, of course. So if you spot those sort of things, you can save yourself a bit of time. 70 and 70.